Good afternoon. We continue with session 2. The first speaker is Dmitry. Not UXOR type events in AWR Liga и Daugen polarimetric observation. After reading the program, I decided that RWR Riga is covered enough by my colleagues from Moscow University, and I will focus on AA Tauri. As we were told today, AA Tauri is a prototypical dipper, the type of classical Tauri star with quasi-periodic minima, and it also undergo long-lasting fainting event, which still continues. And I will discuss our polarimetric observations of A Tauri before and during the fainting event. That's typical light curve of AA Tauri in normal pre-fainting state. Quasi-periodic minima are observed. Sometimes they disappear, sometimes they appear again. They are not strictly periodic, but quasi-periodic. This means that the shape and phase of the minima varies, but period is well established and it is close to rotational period of the star. This was first established by Bouvier and co-authors, and they supposed interpretation that minima are caused by rub in the inner rim of the disk. The rub is induced by magnetosphere of the star, and as magnetosphere rotates, as a solid body, some parts of the rim screen the star. This was confirmed polarimetrically by Minard and co-authors. This is one of the sets. It's not quite impressive. Photometry is not simultaneous with polarimetry, but nevertheless, this signature, the rise of polarization in minima, is there. It's observed. Later, it was found that this type of variability is very common and probably the most common among classical T Tauri stars. This was this paper by Alesknar and others. The classification is based only on the classification of light curves. That means that we are not sure that all the dippers, so-called dippers, are exactly analogous of A Tauri itself, but they have very similar light curves. And in 2011, brightness of the A Tauri fell, and it is still in this faint low low light state. Bouvier and others analyzed color characteristics of this fainting event and found that event is caused by small dust because, as we can see here, it is redder when in this state, and also that the AV that we estimate from optical photometry is less than AV that estimated from infrared, near infrared. The explanation is simple because here we add some scattered light, and that limits the amplitude of fainting. There is ALMA imaging of this object. The results are not very consistent with earlier determined inclination of 75 degrees. This estimation was from two sources. First is spectroscopy from VSIMS-I estimates and from coronographic imaging. But from ALMA imaging, inclination is about 60 degrees. So this is one of examples of one of the cases of misalignment of inner and outer disks as seen by ALMA. And authors of this ALMA research, they proposed even an explanation for the fainting event that they speculate that probably there are some streams of matter connecting outer disks to the inner disk, and fainting event is the intersection of the stream and line of sight. This is, of course, highly speculative because it's difficult to understand why matter should flow from outer disk to the inner disk in the point of maximum separation of inner and outer disks. But that was the explanation. More conservative explanation by Bouvier is some density bump in the disk somewhere at radius greater than 8 AU. This 8 AU estimate is made from assumption that this clump is in Keplerian rotation, and because we didn't observe another fainting event for 30 years, period should be greater than, say, 30 years. So it's not quite reliable estimate of the distance. This is photometry, sum of photometry of 8 hours during the fainting event. Here are 2 seasons, and red dots are moments of our polarimetric observations. That is, the star was in this faint mode this period when we observed. But first, I'll describe our earlier observations of 8 hours before fainting event. We observed 3 seasons in this range. These all are pre-fainting observations. Basically, they confirm result of Minard's. We observe nice correlation of polarization parameters and brightness, and position and angle is quite consistent with what we expect from the disk scattering using position angle from ALMA imaging. Pink dots are our pre-fainting observations, and we see they're quite consistent with disk scattering model, plus usual contrast effect. But black dots are polarimetric observations during the fainting event, and they are quite different. And you see here that one observation is exactly same polarization as pre-fainting bright state, others with quite high degree of linear polarization up to 10%, and dependence of polarization on brightness is complicated. That is our main conclusion from these observations is that pattern of polarimetric variability changed completely with the onset of fainting event, and we don't have fixed positional angle along which polarization vector varies. It's all over the place. That is, it's almost random angle. The only thing that is more or less regular is a band-to-band correlation of polarization parameters. These are Stokes parameters in E and R band, and here correlation is quite good. What does it mean? Usually, high degree of correlation of polarization parameters means that here we observe single mechanism of variability, and all these seemingly random, irregular changes of polarization, they are caused mostly by geometrical changes, not the physical changes of scattering or other mechanism producing polarization. As for the mechanism and interpretation of this data, they are of course quite speculative, because we If we stick with the scattering mechanism, the geometry of scattering matter should change very fast and radically. That is, we should go from disk shape to jet-like shape and back again randomly, which is not very plausible. And it is even less plausible to produce these changes rapidly with short characteristic time. And in our data, they are changing in days and weeks. And this is not consistent with Bouvier and others' estimations that this extra screen, extra obscuring feature that caused the fainting event should be very far from the star and obscure evenly the star and the inner rim of the disk. Or probably we don't have to change scattering geometry radically, but the screen causing the fainting event is very clumpy, very patchy, and it may obscure different parts of scattering inner disk differently. But in that case, we should observe this patchiness, this clumpiness of screening agent in photometry, because there should be holes in the screen, and we should see some brightenings during fainting event, and that's not observed as we have seen from light curve. During the fainting event, the star is always faint without brightenings. And again, the very well correlated band-to-band polarization parameters, they are argument against a simple model with scattering and contrast effect, because contrast effect always produces variable wavelength dependence of polarization parameters due to because extinction is selective, and in different bands we have different contributions from scattered light into observed light, and it's well-known effect in UXORs that wavelength dependence of polarization is very variable. And of course, we can resort to the mechanism discussed by Boris in previous talk with dichroic absorption by alignment dust grains. But of course, we don't have the hard evidence for that. And besides that, this explanation is very well, dull, because it basically says that everything what matters happens on this small spot on the line of sight, and we can't constrain some properties, some geometry of the whole system from this data. And if we avoid speculative explanations, probably the conclusion from our observations is that the pattern of polarimetric variability changed radically with the onset of long fainting event, and it doesn't fit simple scattering plus contrast effect model. And I think that may be considered extra evidence for proposed interpretation as something different from usual eclipse by the disk rim, by the wrap on the rim, and that this obscuring matter is somewhere much farther from the stars than the inner rim. That's all.
These questions?
Sorry, what you are named contrast effect. What do you mean?
Usual UXOR mechanism for polarimetric variability. We have constant scattered light, we have variable direct light absorbed by something on the line of sight, and polarization rises due to contrast.
And why this effect leads to dependence of polarization angle on wavelengths?
Not position angle, dependence of degree of polarization of wavelengths, because extinction is selective, and it is selective in this case. We have the evidence, photometric evidence.
Other questions? Please.
Did anybody observe a tau in the infrared region during the long fading event?
Yes. I have shown the data. Here. This is from this Bouvier paper.
But this is a cooler, but not magnitudes.
Yes, they observed, and the magnitudes are slightly fainter than before the fainting event. There is reddening too in the infrared.
Next question.
Not a question, but a comment. It would be nice to find a common model for both A Tauri and RW Auriga. In RW Auriga, the disk inclination is about 45 degrees, so the obscuring screen cannot be farther out from the star because of this large inclination.
I don't know about common model because in some sense we have opposite situation in polarimetry. In RW Auriga, before the fainting event, we observed rather chaotic changes, variability of polarization. During the fainting event, we observed rather regular pattern with almost constant position angle. That is, there is a preferred angle, and geometry of the system should be rather stable. And with A Tauri, it is the opposite. Before the fainting event, we observe rather regular pattern consistent with classical UXOR scenario. And during the fainting event, we observe rather chaotic, irregular variability.
Sorry, and inclination, not 45, 58 degrees inclination for A component, according to Alma.
One more question.
Not question, but small comment. First of all, I want to say that the model of the deep minimum for RW Auriga can be explained such even in A tau. I don't understand why not. The strengthening of the dusty disk wind, not far from the star, but very near to the star, but during the long time.
Yes.
During the long time, because during this time the star accrete much intensive than in previous time. This is the first what I want to say. The second, if you consider the system of R tau with inclined inner warped disk, and this disk rotates together with magnetosphere, it produces the shadow, the very white shadow on the disk, on the scattered disk. And this means that position angle of polarization must change during, during rotation of the star.
But this wasn't observed before the fainting event. Maybe the signal to noise is not enough. And now I submitted a proposal to search for this low amplitude polarization variability in other deepers, because A tau is not a usual deeper, but there are other systems, and probably these shadows may be detected polarimetrically, but not detected yet.